Welcome to the second video on confidence intervals for differences in means and proportions across two samples. In the first video, we went through the sampling distributions and constructed the formulas for finding a confidence interval for the difference in two means or two proportions. In this video, I'm going to do a basic example of each of these. I'll also throw in a misleading example that might look like a difference in two means, but it really isn't. And I'll also go through an example where we can use a dummy variable in a regression to construct a confidence interval for a difference in two means. So as a reminder, confidence interval, regardless of whether we're doing a single mean or a difference in two means or a single proportion or a difference in two proportions or also a regression coefficient, we always start with a point estimate and then we add and subtract a margin of error, which is a product of the magnitude of the standard error and the number of standard errors that we need to achieve the desired level of confidence. And all of this information comes from the sampling distribution of our relevant statistic. And this includes the sampling distribution of x bar 1 minus x bar 2, which contains the information we need to construct a confidence interval for mu1 minus mu2, and it also includes the case where we know the sampling distribution of p1 bar minus p2 bar, and we can use that to construct a confidence interval for p1 minus p2. And so we need the sampling distributions. And so just as a quick reminder, the sampling distribution for x bar 1 minus x bar 2 is a t-distribution with degrees of freedom. The smaller of the two sample sizes minus 1, so n minus 1 or n2 minus 1, whichever one is smaller. The point estimate is mu1 minus mu2, and the standard error is the formula given on the screen. And so putting all those pieces together, we have the confidence interval formula. And then similarly for differences in two proportions, that has a standard normal distribution if the sample sizes are large. It's centered at p1 minus p2, and it has sort of that ugly standard error formula, but don't worry about how ugly it is. Just remember the important thing is that it's concrete. We can just plug in the numbers, or we can have some computer program plug in the numbers, and we can get a numerical value, and so we can construct a confidence interval following exactly the same format as for the other cases. So let's do an example. Suppose we have two industries and we're interested in comparing the difference in average wage level across those two industries. And so what we're going to do is we're going to take independent random samples, one random sample from one industry, one random sample from another industry, and use the difference in the sample averages to draw conclusions, make an inference about the difference in the population average. So we have our two industries here, unimaginably called Industry 1 and Industry 2. Again, you can see the details there, the sample statistics from each of our industries, and we want to estimate with 95% confidence the difference in the average wages between the two industries. So the first thing we should do is identify the problem. We want to find a 95% confidence interval for the difference in two means, mu1 minus mu2. And so then the first thing we should do is immediately then write down the confidence interval formula for this case, mu1 minus mu2. So we start with the point estimate. That's the difference in the sample means. And then we want to add and subtract the margin of error. That's t alpha over 2. If we have large enough samples, we know the sampling distribution of x bar 1 minus x bar 2 as a t-distribution. So we want to figure out how many standard errors based on the t-distribution times the standard error, which is the standard error of our sample statistic, x bar 1 minus x bar 2. So we just need to find each of those pieces and then do the math, and we'll have our confidence interval for the difference in average wages between the two industries. Okay, let's also write down what we know from the problem. Now the first thing we would want to do is define what exactly is sample 1 and sample 2. In this case, it's already inherent in the problem, Industry 1 and Industry 2. But, maybe if one of them was finance and another was manufacturing, the first thing we should do is write down like Industry 1 equals finance, Industry 2 equals manufacturing. We want to keep careful track about what Industry 1 represents, or what population 1 represents, what population 2 represents. Okay, so we don't need to do that in this case because it's already industry 1 and industry 2. So what do we know from our sample from industry 1? Well, we know the average in that sample is 1750. We know the standard deviation is 4, and we know the sample size is 46. And then similarly, in sample 2, we know the sample mean is 1825. We know the standard deviation in sample 2 is $3.50. And we know that the sample size is 51. Okay, so we're going to use this information plus what we know about the sampling distribution of x bar 1 and x bar 2 to fill in the pieces over here, and that will give us our 95% confidence interval. So the point estimate is easy. That's just the difference in these two means. So that's 1750 minus 1825, which is a difference of minus 75 cents. Okay, how about T alpha over 2? 95% confidence interval. So remember, little tiny picture. We have 2.5% down up in this tail, 2.5% down in that tail. We have 95% in the middle. Okay, with a T distribution, we always need to remember that we need to know degrees of freedom. In this case, with x bar 1 minus x bar 2, the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1. So let's do n1 minus 1, that's 45. N2 minus 1 is 50. This one is obviously smaller, so this is our degrees of freedom. So we want T 0.025 because we have a 95% confidence interval with 45 degrees of freedom. So we have our familiar T distribution table. We're again in our often used 0.025 column. And now we want to go down to 45. And we find 2.0, would help if I could put it on the screen where you could see it, 45, 2.014. So T is 2.014. If we really wanted to mess up our little figure there, that's between plus or minus 2.014. And so the last thing we need is this standard error. So the formula for the standard error, x bar 1 minus x bar 2 is the variance from sample 1 over the sample size plus the variance, not the standard deviation, but the variance over the sample size. So this is 4 squared, the standard deviation squared, over 46 plus the standard deviation squared, that's 350 squared, over the sample size, 51. If we do this math, it might look ugly. It's just math. It's 0.767. The more complicated the math gets, the safer you are by writing down everything you know, writing down the formula. Then you just have to look back and forth and make sure you plug in the right thing, and then just do the math in the calculator. Okay, so the value of the standard error of the difference between x bar 1 and x bar 2, that sampling distribution is 0.767. So our margin of error is 2.014 times 0.767. And so that gives us a margin of error, if we multiply those two things together, of 1.545. So our 95% confidence interval for the difference in average wages between industry 1 and industry 2 is minus 0.75 plus or minus 1.545, or if we wanted to put that in an interval, minus 2.295 up to 0.795. We're 95% sure that the true difference in wages between industry 1 and industry 2 is between minus 2.295 and positive 0.795. Okay, let's do an example for proportion. So in this case, we have two samples. We have a sample of janitors and we have a sample of engineers. And we're going to ask, how satisfied are you with your benefits? And it's not a very sophisticated scale. We're just going to essentially have you be, yes, you're satisfied. No, you're not satisfied. So the proportion we're interested in is the fraction satisfied, and we're interested in the difference between the fraction satisfied for janitors and the fraction satisfied for engineers. So, what should the first thing, what should we do first? We should identify this. We want a 90% confidence interval for the difference in two proportions, P1 and P2. First thing we should do after that, two quick things. One would be to immediately write the formula, which is the point estimate, P bar 1 minus P bar 2, plus or minus, is it T or Z? Well, proportions, if the sample size is large enough, is Z. So this is Z alpha over 2 times the standard error P bar 1 minus P bar 2. And the next quick thing we should do is identify, if we're going to use 1s and 2s rather than janitors and engineers as our subscript, we should quickly define what we mean by 1 and 2. 1 is going to be janitor, 2 is going to be engineers. Okay, then based on that, we know that P1, the proportion of janitors satisfied, is 0.4. And we know the proportion of engineers, P2, that are satisfied, is 0.52. And so then we also know 1 minus P1 is 0.6, and that's a minus, and 1 minus P2 is 0.48. That's a minus, 1 minus P1. So now, I suppose we could also write down that N1 is 750 and N2 is 400. Okay, so now we want to use this information to figure out the 90% confidence interval for P1 minus P2. So again, we can start with the point estimate, P1 bar minus P2 bar. These are all bars. P1 bar minus P2 bar. So that's 0.4 minus 0.52, which is minus 0.120, plus or minus now Z alpha over 2, 90%, so that's 90% in the middle, 90% in the middle, 5% in the lower tail, 5% in the upper tail. So we want to look at 5% in the upper tail, and in our T thing, this infinity, as we get to infinite degrees of freedom, these are the normal values, so that's 1.645. And then we need to figure out the standard error. Okay, so the standard error, it's a little bit of a mess. Okay, so it's the square root of P1 bar times 1 minus P1 bar over the sample size, and the same thing for sample 2. And so if we do this, right, we're just going to fill in all of these numbers here. This is 0.4 times 0.6 over 750. And this here is 0.52 times 0.48. over the sample size of 400. And if we do all of that, that equals 0.031. We just do the math. It's just math at that point. Write out the formula. We have everything written down. We just fill in. And we can figure out that it's 0.031. So if we come back over to here, what is our standard error? That's just what we found, 0.031. So then this is our margin of error, 1.645 standard errors. That is a margin of error of plus or minus 0.051. So we're 90% confident that the true difference in population proportions, difference between janitors who are satisfied and engineers who are satisfied, is minus 0.12. So we think fewer janitors are satisfied. And we're 90% confident between minus 0.12 plus or minus a margin error of 0.051. If we change that to an interval, that's from minus 0.171 up down to minus 0.069. So we're 90% sure the true difference in proportions is between minus 0.171 and minus 0.069. Okay, same logic as single means and single proportions, same idea, point estimate plus or minus a certain number of standard errors. It's just with two populations, the formulas are a little messier, especially for the standard errors, but it's just math. Don't let that throw you. Okay, let's look at what I'll call a disguised example, right? So we have something that might look like a shark, but it's really just a goldfish. Okay, so the setup here is, suppose a company is considering switching its office location, and one of the factors in that decision might be what that's going to do to employees' commuting time. So you're interested in how long does it take people to commute to your current location, how long might it take to this new proposed location. Okay, so we can try to make an inference here by collecting a sample. So we draw employees at random, and draw employees at random, and we ask them how long it takes them to get to the current location, and we ask them to estimate how long it would take to get to the new location, and we can collect data then, and we can look at the difference, right? And we want to estimate whether we think what we think the difference in commuting time is between the current location and the other location, other proposed location. Okay, so we might have data that looks like this. So for employee 1, it takes them 63 minutes to get to the current location. It would only take them 40 to get to the proposed. For employee number 2, 72 to the current location, 59 minutes to proposed, etc. Right? And this might look like we have two samples, and so we could do the same kind of confidence interval like we did here, right? But this is really sort of disguising the true nature of things, right? You don't have two independent random samples. It's not like you sampled a bunch of employees and asked them how long does it take to get to the current location, and then took a completely different sample and asked them how long it would take those individuals to get to the new location, right? You didn't draw two random samples. In fact, you just drew one random sample and happened to collect two pieces of information. And really what you're interested in is just the difference. Right, and so what we're really interested in is just the difference between these two. And so what we really should do is just calculate a third variable, and then we have sample statistics, we have mean, standard deviation, sample size for this variable here, and we're really not interested in those variables at all. They're just means to get at what we're really interested in. What we're really interested in is the difference, and in this way we really just have a traditional single mean case, and we just would use the normal single mean confidence interval techniques to to calculate a confidence interval for this average difference. Okay, so it might look like you have two samples, but you really didn't take two samples. You really only took one sample, and you're interested in a difference variable. So it's really just a classic one sample case. Don't let the disguised example throw you off. Okay, one last example. Let's go back to our first example of the wages in the two different industries, and let's think about doing this in a regression framework instead. So here we have our data from industry 1. Here we have our data from industry 2, an average of 1750 in industry 1, an average of 1825 in the other. Well, let's think about doing this in a regression. Now we can't run regression with the data in two different columns, so we need to stack it. So notice what I've done here is I've stacked it. So I brought all of these over here and marked them as industry 1. And if we go down far enough, then these people from industry 2, right, they're down over here, and I've stacked them. And so we have the industry 2 wages in the same column as the industry 1 wages. And so now what I've done is I've created a dummy variable. All right, so just using like an if, and we're going to make a dummy variable which will indicate everybody who is a yes for industry 1. And so all of these industry 1s get a dummy variable 1 here. And when we get down here for industry 2, our dummy variable is 0, right? So a very classic dummy variable. It's 1 for those who are industry 1 and 0 otherwise. And so now we could run just a regression where wages are dependent variable, and wages are dependent variable, and our industry dummy variable here is our only independent variable. And so let's look at our regression results. 97 observations, because we pooled the 46 and the 51, and we just have two variables. We have intercept, and we have the dummy variable for industry 1. Okay, now let's go back and remind ourselves the interpretation of regression variables. Intercept, that's the predicted value of the dependent variable when all of the other variables are 0. So in this case, that is the predicted value for industry 2, because that's when this is 0, that's industry 2, and we get 1825. And in fact, that's exactly the mean in industry 2. Now let's look at industry 1. So that's a dummy variable, and so that's going to change our predicted value for everybody when this is 1. So that's going to change the predicted value for industry 1. And so on average, this is saying that industry 1 wages are about 75 cents lower than industry 2. And in fact, that's exactly what we find with the mean difference, 1825 and 1750. All right, so again, now if we had other control variables, we wouldn't expect to get exactly these numbers, because they'd be, holding constant, maybe gender composition in the industry, unionization rates in the industry, right? And so this intercept then would be with 0 unionization and 0 women, or however we had our variables coded. But with nothing else in the regression, we'd expect exactly what we have here. This intercept is the average wage for industry 2, and this is the difference. And in fact, that's exactly the difference we got when we did our confidence interval over here. Okay, and so if this dummy variable is picking up the average difference between industry 1 and industry 2, then remember we can do a confidence interval for a regression coefficient, and since this regression coefficient is picking up average difference between industry 1 and industry 2, then the 95% confidence interval is a 95% confidence interval for exactly what we're looking for over here, a 95% confidence interval for the difference in averages between the two industries. And so here's our 95% confidence interval over here from the regression. Notice that is fairly close to what we found here. For minus 2 point over, when we did it, the sort of traditional way or did it by just directly doing a formula for the confidence interval, we found minus 2.295 to 0.795. Over here in our regression, it's close, minus 2.26 instead of about minus 2.3. Now there's a, you might have expected these to be identical. Well, there's two things going on. One is there's a degrees of freedom issue going on. Remember over here, treating each sample independently, we use 45 degrees of freedom, whereas over here they're pooled, so we're using 95 degrees of freedom. So there's a difference there. There's also another technical difference in terms of how the standard error is calculated, but both of those differences really get quite small as you get a few hundred observations. And so if you had, say 400 observations in each industry, there'd be no difference between what we calculated over here and over here. So if you're using like an enterprise data set and have lots of observations, an easier way perhaps to look at average differences between two groups would be to just run a regression rather than doing this confidence interval. Another advantage of doing a regression is you could do adjusted means as well. So again, we could do mean difference between industry 1 and industry 2, controlling for other features in that industry if we did if we added more control variables and did a multiple regression. Right now we're just looking at the unadjusted wage, and that's why we got exactly these numbers replicated by our regression coefficients. So in conclusion, right, it's common to have situations where we have, say, two different samples or two different groups within a sample, and we want to compare differences in means or differences in proportions. And this video and the previous one has meant to illustrate that we can use confidence intervals that are exactly the same logic, exactly the same processes in the single population case, and we just use x bar 1 minus x bar 2 or p bar 1 minus p bar 2, right, the difference in sample means, the difference in sample proportions, to construct confidence intervals for the difference in two population means or two population proportions when we have two independent samples. So that follows exactly the same logic as other types of confidence intervals. But a warning, remember, match pair can sometimes, be sort of a single population in disguise, and it might look like it's two populations or two samples, but it really is one. And so the question comes back, do you really have two different independent samples, in which case it really is a case where you have to do you really have to estimate mu1 minus mu2, or is it really just you've collected one sample and you've collected two pieces of information, but you're interested in the difference? If that's the case, then that's what we're calling match pairs, and that's really just a single sample or single population case. It really isn't a case of two different independent samples. And then as a final concluding note, remember that we can use dummy variables to examine average differences across different groups. And if you do that in a simple linear regression where you don't have any other control variables, right, that's the same thing as looking at unadjusted mean differences. So that would be the same thing as looking at mu1 minus mu2. And if you add in control variables, you can think of that as adjusted mean differences, right? The difference in wages across two groups, adjusting for differences in education or years of experience or things like that. And that would be with a multiple regression.